So hi everyone, I'm Kendra. I'm a graduate student at Yale, and I'm here to tell you about some misaligned Saturns. So with the discovery of thousands of planets, close-in giant planets have really been challenging theories of planet formation. The core accretion model predicted that gas giants should form further from their host star in order for volatiles to accrete. However, hot Jupiters have been found with orbital periods of less than 10 days. As a result, new theories have been formed to explain hot Jupiter formation through high eccentricity tile migration, in situ formation, or disk migration. Another surprise is the range of orbital architectures that have been reported, such as planets on retrograde orbits. And there's been a lot of recent efforts to obtain orbit measurements for gas giants in order to characterize their orbital architectures. Spin orbit measurements are very useful for getting insight into the dynamical history of systems. So let's get into what exactly I mean by a spin orbit measurement. So first we have a star with a spin axis, and then we'll have a planet in orbit. The orbit normal axis refers to the axis perpendicular to the plane of the planet orbit. The spin orbit angle is then the angle between the spin axis and the orbit normal axis, which is called psi here. This example is of a line system where psi is equal to 0. And our solar system is actually a really good example of an aligned orbital system. And the spin orbit angle for our system is actually about 6 degrees. But a range of spin orbit measurements have been found, and with systems being characterized as misaligned. So an example you see here on the right, we have an example of where psi is equal to 90 degrees, and this is actually referred to as a polar planet. So how do we actually get these spin orbit angles? So stars will have a blue shifted and red shifted side as they rotate. As a planet transits, it will block parts of the star's Doppler shift in its spectrum. We're going to then take the RV measurement as it transits in order to observe what we see as the Rosner-McLaughlin effect here. So on the left side, this is an example of an aligned system. And on the right side, this is a misaligned system with psi about 60 degrees. And it's important to note that when we're doing these RM observations, what we're actually getting is the sky projected 2D spin orbit angle and not actually psi. So I'll explain that difference here. So we have the stellar inclination I, which is the angle between the stellar spin axis and the line of sight. And then we have the planetary orbital inclination, which is the angle between the orbit normal axis and the line of sight. Once again, psi is the angle between the orbit normal axis and the stellar spin axis. And when we measure Rosner-McLaughlin from a Rosner-McLaughlin observation, what we get is the 2D sky projected angle lambda. And so I plotted here all known measurements for hot Jupiters around hot stars. On the on the x-axis is the stellar effective temperature, and then on the y-axis is lambda. On the right side here is the distribution of hot Jupiters. The gray area you see on top, it just refers to a planet on a retrograde orbit. So you can see that hot Jupiters are misaligned as to higher temperatures. However, when we plot our measurements for warm Jupiters, you can see that warm Jupiters are more aligned than hot Jupiters. The alignment of warm Jupiters has been explained by the convective envelope around cool stars realigning the warm Jupiters. So the misalignment trends for hot Jupiters and warm Jupiters have prompted different theories for how they evolved. So with hot Jupiters having a history with high eccentricity migration with tidal damping, while warm Jupiters have a more quiescent history with primordial alignment. So our measurements have been biased towards Jupiters, but now with high precision RVs, we can now extend these measurements down to Saturns. A big question is whether Saturns experience higher rates of planet-planet scattering compared to Jupiters. And another important thing to note is that this 0.3 cutoff for Jupiters is actually not physically defined. And in our solar system, Saturn is actually about 0.3 Jupiter mass. So the question is then, is there a way that we can use spin orbit measurements and dynamical histories to characterize and distinguish Saturns from Jupiters? So going back to our Jupiter's plot, I've also added sub-Jovian planets here. And for our case, I've actually defined sub-Jovians as less than 0.4 Jupiter mass, and hot Jupiters and warm Jupiters as being greater than 0.4 Jupiter mass. You can see that it's very interesting how Jovians are more misaligned than Jupiter's, especially around cool stars. And so this misalignment trend for Saturn's has been thought to be primordial alignment, and then these Saturns are misaligned through planet scattering or secular interactions. For our sample, I've defined Saturn as 0.2 to 0.4 Jupiter masses. And ultimately, the question we're trying to answer is, what are these boundaries between Saturns and Jupiter masses? Saturns and Jupiters as defined by their dynamical history. For our study, we focus on 3 targets. You'll notice that these 3 targets are all around cool stars. You might be wondering why TOI 2123 doesn't have a mass measurement. That is because our RV measurement reviewed transit time variation signals, and therefore we chose to do further analysis in a separate paper. But we were able to obtain RM measurements for all these 3 systems, and we supplemented our RM measurements with additional archival data. And we've used our combined datasets in a joint fit, and the preliminary results are displayed here. So on the left side, we have the archival photometry. The middle plot is of the archival RV measurements, and then the left side is our observations with one additional RM observation from Knustrup et al. 2024. You notice that K2261 is misaligned, while TOI 1175 and TOI 2123 are aligned. However, we can actually calculate psi for these planets. And since TOI 1775 displays stellar activity. So since it has stellar activity, we're able to use the test light curve to find that it has a stellar rotational period of about 6 days, and then use Masuda and Nguyen 2020 in order to calculate the stellar inclination, and then use Fabricate and Nguyen to calculate the psi. And we actually found that TOI 1775 was misaligned. Likewise, we performed the same measurement for TOI 2123 and find that TOI 2123 is also misaligned. So let's put these measurements back in the plots from beginning for more context. We can see that these new measurements contribute to a growing sample of misaligned subjovians. So our new measurements are here. And this is especially noticeable if we instead compare stellar effective temperature versus psi. And so our 2 new measurements here, and you can see that these 2 new measurements greatly add to the sample of misaligned subjovians. Another important thing to note is that there is this bimodality on the right side here, which agrees with Albert et al.'s 2021 paper on the preponderance of perpendicular planets. The misalignment at lower planetary masses suggests longer realignment timescales, where the convective envelopes of cooler stars have yet to realign with the subjovians. Likewise, we also considered spin orbit angles versus A over R star. And we can see that the misalignment extends to further A over R star here, compared to the population of Jupiters. Once again, if we consider psi, we can see that there are higher rates of misalignment extending to further A over R star, once again, compared to hot Jupiters, which suggests higher rates of planet-planet scattering for Saturns. So overall, I'll leave you with a summary, but misalignment around cool stars and at a range of distances from the host suggests a high rate of dynamical excitation for these smaller planets. And I'm happy to take questions now and to chat further about our work on our measurements. Thank you.